Okay, 2.24 is pretty disgusting to do, primarily purely just because of the p squared calculation. But the other ones are pretty simple, so we'll start easy. So starting off with the expectation value of x, this is going to be, let's see, m alpha h bar squared times the integral from negative infinity to positive infinity of x e to the negative 2m alpha magnitude x dx, or whoops, over h bar squared and then dx at the bottom. Remember, the expectation of any operator q hat is going to be the integral from negative infinity to infinity of psi star times q hat acting on psi. In this case, since our wave function has no complex terms in it, this is effectively the same thing for x as just x times mag psi squared, which is why we're squaring everything. Instantly, you should see, hopefully, that this term right here is odd, just from, looking at this, right? This term is even, just from looking at the graph. So this is even because it's symmetrical about the y-axis. So x itself is odd, so that means this entire expression is going to be odd. So automatically, since we're dealing with, a symmetric integral of an odd function, this integral automatically, just by definition, is going to equal 0. So that is the expectation value of x taken care of. Next thing is x squared, which is a bit harder, but still relatively simple. We have the same process, m alpha over h bar squared, integral from negative infinity to positive infinity, this time x squared e to the negative 2m alpha magnitude x divided by h bar squared dx. The difference here, or not the difference, or yes, the difference. The difference here is that we have an x squared at the bottom here, and then we have a magnitude x at the top in the exponent. Both of these terms don't care if x is positive or negative, so we can take advantage of symmetry here and just multiply a 2 at the front, m alpha divided by h bar squared, and change our integrand from 0 to infinity. And then we have x squared e, now the magnitude sign's gone, to m alpha x divided by h bar squared dx. From this point, this is just u sub. We have u equals x squared, du equals 2x dx. We have dv is equal to e to the negative 2m alpha x divided by h bar squared, and we have dx as well, and then we have v equals negative h bar squared over 2m alpha multiplied by e to the negative 2m alpha x divided by h bar squared. And from this point, we have 2m alpha divided by h bar squared, and then we have, starting with uv, well, this is going to be x squared, or before that, let's write the constants at the front first. Negative h bar squared over 2m alpha x squared e to the negative 2m alpha x divided by h bar squared, evaluated from 0 to infinity, minus integral of v du. So it's going to be plus the 2 at the top and the 2 at the bottom cancel, h bar squared over m alpha, and then multiplied by the integral from 0 to infinity of x times e to the negative 2m alpha x divided by h bar squared dx. First off, here at positive infinity, the exponential goes to 0. At 0, x goes to 0. So in both cases, this term is just 0. The boundary term doesn't mean anything here. It cancels out. What we have left is just 2, because we have 2, and then m alpha cancels with m alpha at the bottom, h bar squared cancels with h bar squared on the bottom. 2 times the integral from 0 to infinity of x e to the negative 2m alpha x divided by h bar squared dx. This is the exact same u sub process that we did before. So I'm just going to copy this and move it down here. The only difference is that we're working with x squared, or we're working with x instead of x squared. So du just becomes dx and u is equal to x. From this point, if we substitute this in, then what we get is that we have 2, and then uv, which is negative h bar squared 2m alpha times x e to the negative 2m alpha x divided by h bar squared, evaluated from 0 to infinity, minus integral v du. This is going to be plus h bar squared over 2m alpha times the integral from 0 to infinity of e to the negative 2m alpha x divided by h bar squared dx. Same thing for the reason above. This boundary term is just going to go to 0 because x goes to 0 at 0 and the exponential goes to 0 at infinity. What we have left is h bar squared over m alpha times the integral from 0 to infinity e to the negative 2m alpha times x divided by h bar squared dx. This is just an easy integral that we can just do immediately. H bar squared over m alpha, and then we're multiplying by, let's see, h bar squared over 2m alpha, and we attach a negative at the front. And what we have now is the same exponential, e to the power of negative 2m alpha x divided by h bar squared, evaluated from 0 to infinity. This is going to give us negative h bar to the 4th over 2m squared alpha squared. And then what we have here, at infinity, this is equal to 0, and then subtracted by, at e to the 0 is just 1. So this is equal to h bar to the 4th over 2m squared alpha squared. And let me just double check that that's correct. It is indeed. Okay, so we have x and x squared. The overall goal is to calculate the uncertainty principle, so let's start just by calculating delta x real quick. So this is square root of the expectation value of x squared minus the expectation value of x term squared. Do a square root here. This is just going to be equal to the square root of h bar to the 4th over 2m squared alpha squared. That is going to equal h bar squared over m alpha square root of 2. And that is delta x. Next, we start working on p's. Thankfully, the expectation value of p is actually very simple because we can actually use Ehrenfest's theorem, which we derived back in chapter 1 in one of the earlier problems, which says that the expectation value of p can be written as the derivative of the expectation value of x with respect to time. And since the expectation value of x is just 0, the expectation value of p is also sort of just 0. Now, let's set up p squared. So first off, p hat is equal to negative I h bar d by dx. So that means p hat squared is going to be, let's see, 2 negatives make a positive, 2 i's make a negative, negative h bar squared d2 by dx squared. So if we write that in, the expectation value of p squared is going to equal, first off, all our constants at the front end up getting multiplied. So we have m alpha divided by h bar squared, and we have our integral from negative infinity to infinity, e to the negative m alpha magnitude x divided by h bar squared times d2 by dx squared of e to the negative m alpha magnitude x divided by h bar squared dx. Okay, first off, apologies, I realized I made a mistake in setting up the p squared system. I forgot to include the negative h bar squared at the front, so once I do that, this is going to be negative m alpha at the front. Second, so the way that Griffiths wants us to solve this is he wants to take advantage of the property we discovered in 2.23b, which is that the derivative of a step function is effectively equal to a, what do I call it? It's effectively equal to a Dirac delta. So what I'm assuming that he wants us to do is he wants us to define a step function theta, which equals either positive 1 or negative 1, depending on which side of the axis we're on, whether x is negative or positive, and sort of rewrite this magnitude expression by getting rid of the magnitude and introducing this sort of step function. I don't really like doing that because I feel like it adds an extra layer of complexity by introducing this sort of thing. So instead, I'm going to solve this using my preferred method, which, first off, to do this, I'm going to start by sort of recognizing the fact that, okay, derivatives of absolute value functions are tricky, and I really don't want to do more than I need to. So I would really prefer if I could somehow mold this equation to look more like a single derivative function instead of a second derivative, because I really want to avoid taking more derivatives of magnitudes than I have to. So immediately, what I'm going to say is that I can recognize this as a function f of x multiplied by the second derivative of that function, d2f by dx squared. And I can massage this by using u sub, because if I say that, okay, u is equal to f of x, then du is equal to df by dx multiplied by dx. And then we have, if dv is equal to d2f by dx squared dx, then v is equal to df by dx. So immediately from this case, we have that the expectation value of p squared is going to equal negative m alpha multiplied by, let's see, uv, which is going to be f of x df dx evaluated from negative infinity to positive infinity, minus the integral of v du, which is going to be the df by dx squared from negative infinity to positive infinity dx. And what we see from here is that Well, f of x is equal to e to the negative m alpha magnitude x over h bar squared. Regardless of x is negative or positive, the magnitude forces it to be positive. And we see that at positive infinity, this is e to the negative infinity. Automatically, this boundary term just goes to 0 because f of x is equal to 0 at infinity and negative infinity. What we have left is m alpha times the integral from negative infinity to positive infinity of the second derivative, df, or the first derivative, df by dx squared multiplied by dx. This is significantly easier to do than taking the second derivative, so we can work from here. And to sort of resolve the magnitudes, we can split this into two integrals. So what we do here now is we recognize that this is m alpha multiplied by the integral from negative infinity to 0 of d by dx of e to the, and here we see, okay, this top term always has to be negative. M and alpha are always positive, so if x is always negative, we can just forego the negative at the front here and just write this as m alpha x divided by h bar squared. And then we want to square this term, multiply it by dx. So the reason why we're getting rid of the negative is because since x is always negative, sort of the negative sign that was up here is now intrinsically contained within the x. Then we add from 0 to positive infinity. And what this is now going to be d by dx. And now, remember, this always has to be negative. M and alpha are both positive. If x is also positive, we now need an explicit negative sign at the front. So e to the negative m alpha x divided by h bar squared dx. And from this point, we just have to evaluate these. These are relatively simple problems to do. So we have m alpha, and then we have our integral from negative infinity to 0 of, let's see, m alpha divided by h bar squared times e to the m alpha x divided by h bar squared dx plus the integral from 0 to infinity of negative m alpha over h bar squared times e to the negative m alpha x divided by h bar squared dx. Close off the brackets. We can immediately sort of take the square of this and distribute it out. So what we have is m cubed alpha cubed divided by h bar to the fourth multiplied by the integral from negative infinity to 0 of e to the m alpha x divided by h bar squared. We add a 2 now at the front, dx minus the integral from 0 to infinity of e to the negative 2 m alpha x divided by h bar squared dx. And now we can just do these integrals. So this is going to give us m cubed alpha cubed. I wrote this as squared when it's supposed to be cubed. H bar to the fourth, and then we have, let's see, h bar squared over 2m alpha, e to the 2m alpha x divided by h bar squared, going from negative infinity to 0, subtracted by, well, in this case I'm going to cancel out the two subtractions, and I'm going to get added with h bar squared over 2m alpha, e to the negative 2m alpha x divided by h bar squared, going from 0 to infinity. Is that correct? The negative at the front cancels out. Yeah. Immediately, we can pull out an h bar squared and also the 2m alpha. So this is going to give us m squared alpha squared divided by 2h bar squared. And then we have, let's see, the exponentials. So at 0, this is just 1, and then subtracted by negative infinity, which is going to give us 0, plus at e to the negative infinity, 0 subtracted by 1. I am doing something wrong here because this is canceling out to 0. Please give me 1 second. Okay. I see where I did wrong. This term right here, because of the fact that it's squared, the negative sign doesn't actually matter. So this is actually supposed to be a positive, and therefore this term is supposed to be a negative. So that means that this bottom term is also going to be a negative. And then this is going to give us m squared alpha squared, 2h bar squared, and then 1 plus 1, which is equal to 2. That's going to cancel out the 2 at the bottom. This is going to give us m squared alpha squared over h bar squared. And respectively, delta p is going to equal the square root of the expectation value of p squared minus the expectation value of p itself squared. This is just going to be the square root m squared alpha squared h bar squared which is going to be m alpha over h bar. From here, we have now the two sort of uncertainties, so we can multiply them together for checking the uncertainty principles. The standard deviation of x, or the error in x, times the error in p, is going to be equal to, what's x? It was h bar squared over m alpha root 2. H bar squared over m alpha root 2 multiplied by m alpha over h bar. The m alphas cancel, the h bar cancels with the 2. We have h bar over root 2, or by convention, since we write square roots at the top, this is going to be h bar root 2 over 2, which is indeed greater than the minimum value of h bar over 2. So therefore, the uncertainty principle is indeed satisfied, and we are done with problem 2.24.